today, in light of what we talked about yesterday, we are going to take a pause from moving forward to review some stuff backwards to prepare us for what we'll talk about tomorrow. So we are going to talk about the characteristics of the graph based on what we did yesterday. Remember where we said, oh, this one's an up-up function or an up-down function. We talked about end behavior. We're also going to look at how the zeros of a graph and how we can use those in order to graph this thing. So by warm-up, I had you guys solve the following equation by factoring. Make sure to use the zero product property because you can take the shortcut, but I'd rather us, just for the sake of benefit our process here, to go through the whole snowflake and zero product property. So in this case, we have a -2 and a -8 that multiply to 16 but add to -10. So here's the zero product property in action, where we write the factors and then we split the factors using the zero product property. Okay? And now solving individually, you get a +2 and a +8. Now some people know the shortcut from here is just to take the opposite reciprocal of what you see here and the opposite reciprocal here, or simply opposite here and opposite there. But I did want us to use the zero product property right here, the ZPP, in order to see how it applies not just to quadratics, but to all polynomials. Okay, next step. You have to graph this thing. All right, so when I punch this thing into your graphing calculator, in this case on Desmos, notice what I get. I do want to point out that it's important for you while you sketch to actually get some things right. Because a sketch isn't just us randomly doing the parabola, but it's actually getting some of the things right. So I'm going to hold on to those things that I just saw there, and I want to make sure that when I translate it over into my graph, things actually line up pretty well. Notice that here is 5, -9. So here is 5, -9, somewhere about there, right? I see that my X-intercepts are at 2, 0 and 8, 0. So I'm going to, plot those points. And then lastly, I see that this 16 is up there, which is off-grid, so I'm not even going to bother doing it. But when I make this fit, I do want to make it fit nicely. Something like this, trying to make the curve fit well without having the lines look straight and arrows at the end. So notice my approximate sketch actually has accuracy. It's not just, oh, look, I sketched it, woohoo, that's it. It's not that simple. Actually get some of the points in that are accurate. So to summarize here, the end behavior is up, up because of the x squared there. The 2 tells me it repeats. The negative, the positive in the front tells me it ends in the upward direction. How do the X-intercepts relate to the factors above? They either zero out the factors or they're the opposite of what I see. And lastly, where's the vertex relative to the X-intercepts? Here are my X-intercepts. My vertex is at the midpoint and above or below. So we're going to use that information here in order to graph our functions today. So first off, describe, then graph the function. So what's the behavior of this right here? How do we expect this one to move? Good. Up, up. This end behavior is up, up. Okay? Next. In order to find the factors, I'm going to use Snowflake. Now, mind you, not every single thing will factor with Snowflake. Sometimes we'll do GCF. Sometimes it doesn't factor at all. So for the problems that we will give you, most likely Snowflake will work. So I put 2 x's in the wings and -8 on top, -7 on the bottom. And let's see what we get here. Looks like -8 and +1. Good. And this one reduces here to be x over -4. So here's a factor, x minus 4, and 2x plus 1. So I found the factors, 2x plus 1, and x minus 4. equals 0. So those are my factors. Now I'm going to solve each one using the zero product property. And I get negative 1/2, and x is 4. Now, next step, I found the factors. Now I'm going to plot the zeros. These right here are my zeros, also known as your x-intercepts, also known as your solutions, also known as your roots. So x is negative 1/2 is right there, and x is positive 4 is right there. Is one of them negative? Yep, thank you. So let me clean that up. Bloop, bloop, bloop. So negative 1/2 is here, and positive 4 is there. Since we know exactly where the vertex is, it's just sometimes mathematically complicated. So watch this. See this here? I know exactly where my vertex is. It's directly in the middle, and in this case below, because this thing has an up-up behavior, end behavior up-up, so the vertex is below there. So let me see here. In this case, I have an up-up behavior also. So that means my vertex is somewhere down here. But notice where the midpoint is here. The midpoint is like right there, which is a number I don't like. Why don't I like that? Because it is 1.75. And substituting 1.75 in by hand, or 1 3/4, gets more complicated, right? So for the sake of simplicity, I'm going to choose either the vertex or one pretty darn close, okay? Because right now, when we're sketching it, we're not worried about 100% about all accuracy, but we want to be approximate. So that's why I chose this near here. So in my situation, instead of choosing the 1.75, I'm going to choose something close, which is 2. So that's going to be close enough, because 2 is easier for me to manage by hand. If I were doing this 100% on calculator, then this is not a problem. But let's just do this by hand and show where it goes. Okay, so when I plug in a 2 into my function, this is my result, and minus 4. Now let me simplify here to get 2 times 4 minus 14 minus 4, and all of that is 8 minus 14 minus 4, negative 10. Which now means instead of the 1.75, I'm slightly over to the right, and I'm down here at negative 10. So I know that my vertex is somewhere here. It's somewhere slightly to the right or left. So when I do make my graph here, this is going to be a tight graph there. I'm going to actually have it drop just slightly next to it. See how I did that? Just slightly next to it, and then come up like that. And arrows on the end. Of course, the arrows on the end result from the up-up end behavior. My vertex I approximated down there, and that's okay because I'm pretty darn close. I know that this is really close to it, so I just dropped it slightly under. And these guys here are actually very accurate. So this is what my graph looks like. Just to review, what did I do? I found the factors and I plotted those, or the zeros, as zeros. Then I either found the vertex or found a very, very close approximation for the vertex. Plotted that and was able then to just make it fit inside. Okay? By way of an example, let's look at number 1. We already did the previous one. So let's just walk through and double check your work with this. So I'm going to set up my snowflake here. So negative 63 and positive 2 and x's in the wings. And we're going to end up here with 9 and 7. So x plus 9 times x, and I messed up, there's a negative 7 there, equals 0. When we do the zero product property, we said that x is negative 9 and that the other value of x is positive 7. So when thinking about our steps, number 1, we factored it. Number 2, we're going to plot the zeros. So where does negative 9 fall? Right here. And positive 7 falls right there. Okay, now what we saw earlier is I don't know how far this is going to go down. Now, first off, I do know it's going down because of the behavior of the graph here. The end behavior is up, up. So because of that, I know that there is an up function here, up here. The question is, how far down does it go? Or does it not? What if it just is very shallow and hangs out here? So what I have to do is choose a point that's pretty close to the vertex. Sometimes I'll choose exactly the vertex and sometimes not. So I know that the vertex is exactly in the middle, in between here. So between here and here, and if we just eyeball it, we see that it's a negative 1. So here's the midpoint, which is going to be where the vertex will lie. The question is, where on this axis of symmetry is my vertex going to be? How far down? So what you have to do is I'm going to take that negative 1 and I'm going to substitute it into the equation there. So x equals negative 1. So y is negative 1 quantity squared plus 2 times negative 1 minus 63. Okay? Keep working through this, yada, 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 to get a negative 64. So now I actually have negative 64 right there. So when I graph this function, I see that it's an up-up function, and it drops all the way down to the negative 64, and it's going to come up now through the positive 7 and arrows on either end. So what 3 things did we do? Number 1, we found the zeros by factoring it. That's 2 things. And then third, we found somewhere in the middle, as close to the vertex as we can. In this case was exactly the vertex. And I found another point right there. So finish up these ones here, 2, 3, and 4. By way of preview of how we're going to use this later, notice that here's a cubic trinomial, that's a function, and it can be rewritten when we factor it to look like this. Now I do want to point out to you that if we use the zero product property, x is 0, x minus 5 is 0, and x plus 2 equals 0. When we solve each one of these, we get x is 0, x is 5, and x is negative 2. And dun 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 dun, x is 0, x is 0, x is 5, x is 5, and x is negative 2, x is negative 2. So notice what's important here is that my factors and subsequently my solutions, or my zeros, are part of my function. They're my x-intercepts right there, my graph. Next, what we just did was say, hey, my vertex is somewhere almost directly in between. And as you notice here, if I were to look here, exactly in between is right here, and that's almost to what we might call a vertex. This is actually called a maximum, but it acts as a local vertex. All right, what about this one here? If I were to go exactly in between these two numbers right here, it's 2.5, and 2.5 brings me, oh my goodness, pretty darn close right there to this right here, which is kind of like a vertex, like I said earlier. It's a local vertex. It's actually called a minima, or minimum. So we are going to be considering that in days to come. What's the end behavior? This goes down, up. We know where the zeros are, and I can approximate these just by choosing the point that's very close to in between. All right, make sure you get this all finished. Enjoy.